With over 1,100 active licenses, KAPA Emeraude is the industry-standard software platform for production log interpretation shared between all major service companies, most operating companies, and independent contractors worldwide. Data from any PL string can be analyzed, from the simplest injector to the most complex multi-probe strings run in a multi-phase horizontal wells. The following example looks at the steps involved in the interpretation of a near vertical well with three-phase flow using what we may call a conventional PL tool string. The session uses files which are available under the Examples folder in the installation. Initializing a new document, Emeraude prompts the user to create the first survey of the session. Surface rate data recorded during the PL job may be included as a constraint in the calculation routine. The workflow for production log interpretation starts by loading the general or static well data. Some completion details are required. So for this particular well, the internal diameter and the perforation depths are loaded manually from the well details icon. Markers may also be added. Open hole logs, such as gamma ray, are loaded for depth matching purposes, or simply to add extra petrophysical information that may contribute to the interpretation. A simple well schematic can also be created to facilitate the display of the data. Typical well components are listed on the right, and they are easily combined to provide a quick well diagram. Once the static data have been loaded, we can load the PLT data files in LIS, LAS, or ASCII format. These can be versus det as passes or versus time in the case of stations. The index and pass direction have to be defined. Once the mnemonics and units have been recognized, all the files can be loaded simultaneously. The scales, data ranges, and layout can be easily adjusted to suit the interpreter. The tracks can be manipulated from the track headers. The current layout may be saved by taking a snapshot of the workspace. Emeraude provides built-in display templates for some tool vendors. In production logging interpretation, data quality control and editing is a fundamental step. From the Edit QA/QC tab, the curve is activated interactively using the Pick Nearest option. Comprehensive editing operations may be applied to bring the data to an interpretable condition. These include filtering, hiding, multipliers, and offsets, etc. In this case, an average filter is applied to the gas holdup data to reduce the noise. Depth matching is performed interactively by comparing the position of the PLT gamma ray, or CCL, to those loaded as reference logs. All the passes can be depth matched individually in this manner. As measurements are a function of the tool parameters, the tool information specific to the survey must be defined. In this example, we define the density tool and the spinner blade diameter. Once the PLT data have been loaded and checked, we can create a new interpretation. Two interpretation methods are offered. The first is the zone method, where the rate calculations are done at specific stable intervals. Here, the user can choose between a strict or loose slippage compliance that may allow the holdup to depart from the correlation prediction. The second is a continuous method, where the rate calculation is done at all points on the log. We will proceed with the zone method with strict slippage compliance. From all the passes available, we need to define the single reference channels that will actually be used in the interpretation. In this case, the available measurements are pressure, temperature, gas holdup, water holdup, and density. Even though there is a redundancy in the holdup data, we will use all the available inputs. In order to convert the spinners, RPS, and cable speed to fluid velocity, we need to calibrate the spinner in a different fluid mixtures. Regions of stable RPS and cable speed and constant fluid type are located in order to compute the spinner parameters. In the spinner calibration cross plot, we obtain the slope and threshold interactively. Clicking on all points, a cloud of points included in the calibration interval is displayed, instead of the single average point. Data may be removed from the calibration plot if necessary. In this case, constant positive and negative thresholds will be used. The spinner calibration application zones are also defined from this window and allow the user to accurately define the regions of application of the different calibration zones. Once these parameters are defined, we can move to the apparent velocity generation, selecting the passes that we want to include. A cutoff option is available to remove points below a certain threshold that lie in the nonlinear calibration region. Once done, interpretation, velocity, density, and water and gas holdup match logs are all generated. The next step is the PVT definition. PL analysis is very sensitive to PVT. A black oil PVT model is used, where we need to select the fluid system and define the main parameters, such as oil and gas gravity and water salinity. The PVT correlations may be constrained using laboratory data, as shown in this case for the bubble point pressure. Before computing the rates, the calculation intervals and inflow zones are defined. In this case, an interactive method is used. Note that for the middle perforation, more than one inflow zone is used in order to achieve better resolution, as a perforation is not producing homogeneously. Although the user has full control over the choice of flow model, based on the PVT input, a fluid model will be proposed by Emeraude. Different multi-phase flow correlations can be used to estimate, together with the holdup tools, the flow regimes, individual phase holdup, and slippage velocity. The flow profile is created, showing the cumulative production and the contributions of each inflow zone. In this particular case, some inflow zones show the production of one phase, while simultaneously displaying the injection of another. Clearly, this is not physically possible. This is a consequence of computing the rates independently at the rate calculation zone level. Therefore, coming back to the rates calculation, under the Contributions tab, we can run a global regression. This allows us to minimize the error of all zones simultaneously and also add constraints. In this example, we force all contributions to be positive. Report creation is quick, automatic, and can include the results and interpretation inputs. This concludes the introduction to the Emeraude Production Log Interpretation module. To learn more about Emeraude or any other KAPA modules, browse our website for literature, more videos, and example data, or contact support at kapaeng.com or your local KAPA office.